Okay, so before starting today, just a little comment about last week. So I got a little bit confused in the last proof when we were proving that Hitting's halting probability is prefix-free incompressible. I was a little bit confused about whether or not I needed to use the fact that the halting probability is irrational in the proof. It certainly is irrational. However, a natural way of proving it's irrational is to first prove that it's incompressible. When we know that it's incompressible, that means it's not computable, and hence it's not rational. So I wanted to avoid using the fact that it's irrational without a proof of that. And after the lecture, I realized how to do that, so I rewrote the notes afterwards. And the proof in the lecture notes, which is basically the same proof as in the lecture, but it's been rewritten in the correct way, that it does not require knowledge in advance that the halting probability is irrational. Okay, well today, last week we did algorithmic information theory. Algorithmic is a great adjective for this course because the course is all about what is computable, and what is computable is about what is an algorithm. So today we're going to talk about algorithmic something else, and it's algorithmic randomness. It's a major topic of research in computability. So that's algorithmic. And so algorithmic randomness is, on the one hand, you can view it as using tools from computability theory to look at infinite sequences of bits and give some measure of how complicated such sequences of bits are in terms of what level of randomness they present, they display. So, for example, a computable sequence would not really be random because we have a deterministic algorithm that generates the sequence, so that has no randomness in it. But can we, to a degree, quantify how much randomness there is in a sequence? And this is done nowadays. One of the tools for doing that is there's a hierarchy notions of randomness. It involved computability theory concepts, which is why they're called algorithmic, or rather why the topic is called algorithmic randomness. And using this hierarchy, you can position a sequence in the hierarchy to say, kind of, has this amount of randomness, but not this greater amount of randomness. Today, we're only going to look at one point in this hierarchy. So one notion of randomness, it's kind of the most fundamental one and the best behaved one, and this is called Martin-Löf randomness. Today we'll look at Martin-Löf already cropped up last week. He was the person that proved that there exists, that no infinite sequence is compressible in the sense of Kolmogorov complexity, which is why we then moved to prefix-free complexity following that. Oh, I just realized I forgot to check if the microphone is working. And today, well, he comes in a big way because he's basically the person that came up with the main definition of them today. For those of you who are kind of interested in foundations of maths and computer science may know the name Martin-Löf from other reasons, because he's also the founder of what is known as Martin-Löf type theory, now just more broadly known as dependent type theory. And this is the main approach to type theory that is now used in some of the main proof assistants that people use for doing formalized mathematics. So proof assistants like Actor and Clock, they're all based on Martin-Löf type theory. So Martin-Löf's a kind of important guy. He occurs in, he's a founder of type theory, but he also, it's a completely separate thing he did. He was the person that came up with the notion of randomness that we're going to study today. One of the things I like about randomness that we're going to look at is that somehow a little bit combines ideas from probability theory and from computability theory. And it's a surprising combination at the beginning, but on the other hand, it's also quite natural, as I will try to explain when we get to that. So we're going to start off just looking intuitively at what we're going to try to describe, and the idea is we want to define the notion of an infinite sequence being random, where random means we could have generated the sequence, it's plausible that we generated this sequence as an infinite sequence of independent tosses of a fair coin. So, right, so the key idea is random sequence. It's kind of equivalent to, want it to be some way of mathematically stating what it's like to say a sequence could have been made by an infinite sequence of independent tosses of mythical fair coin. So, it's probability theory. Okay, so that's the idea of random sequence. Sounds intuitive. I could get a coin out of my pocket, hope that it's fair, and start generating a random sequence. But for what follows, it's going to be more instructive to look at a non-random sequence. So that's because in the end, we're going to give Martin-Löf's notion of a good mathematical definition of random sequence, but that mathematical notion is in a negative form. It says the sequence is random if it's not non-random, and it's easier to give a good story for why that explains why the sequence is not random. So let's look at the simplest, a very simple example of a non-random sequence. So a sequence of infinite zeros. We all agree it doesn't look very random. Now, at this point, for those who know some probability theory, we make the distinction, it's worth making a distinction between probability theory and what we're trying to do, which is say when a sequence kind of exhibits characteristics of randomness. So probability theory would says, well, this could be the result of an infinite sequence of coin tosses, but it almost surely isn't. And so probability theory specifically actually avoids trying to make a difficult definition like this, because in the end, when one's interested in probability, what one's interested in is getting like real numbers out, saying what the probability of something happening or the expected value of something or something like that. So it's kind of irrelevant or not whether we say it's a probability, whether we say that this sequence could, in theory, be obtained as a sequence, as the result of an infinite sequence of fair coin tosses. If we did get it, we would be very doubtful about the fairness, but anyway, nonetheless, according to probability theory, it could arise, but it's kind of the quintessential, simplest example of a sequence that we do not want to classify as being random. Okay, so I'm now going to give a very painstaking explanation for why this sequence is not random. But that painstaking explanation, because it's such a simple example, it will seem painstaking, but at the same time it introduces the concepts that we're going to use and then which will serve us well in more complicated cases. So now I think I should look at my notes just to see exactly how it's phrased. So we're going to justify the non-randomness omega. Well, not the 2 to the omega, but 0. Yeah, but that sequence of infinite zeros. So we have the fact that for any n, the probability that we randomly generate a sequence that it starts with n zeros is what? 2 to the minus n. So for any n, probability, we have the probability that a randomly generated little p, that's our, okay, the first, this is a randomly generated, little p here is a sequence, that's called q. Randomly generated sequence q of coin tosses, the probability that first n tosses are zeros. I always like to have 0 as head and 1 as tail. It's like a head and tail. Coin tosses. So that's 2 to the minus n. And with this observation, we consider the following, what we call a non-randomness test. A non-randomness test is a test we can apply to an infinitely generated sequence that we're getting to detect that it's not a fair random sequence. And the test is based on an error threshold. So we start off with an error threshold and we want to say, we want to certify to up to probability of error epsilon that the sequence is non-random. So given, in this case, given an error threshold, as usual, epsilon is supposed to be a small real number. We perform the following test. First, we find the natural number n such that 2 to the minus n is less than epsilon. We then, this is a test on the sequence q. The sequence in the notes is p, but never mind. More than q. We find an n is such that 2 to the minus n is less than epsilon. We then look at the prefix q of first n values of q, and if q to the n is a sequence of n zeros. We say not random. Epsilon, potential error epsilon, and otherwise we say we don't know because it's not non-randomness not detected. But this is detecting a specific form of non-randomness, but nevertheless, it's something you could apply to a sequence. And you know, one typically takes a value of n like 50, because 2 to the minus 50 is a very, very, very tiny number. So you have the value that we'll take some epsilon like 2 to the minus 50, which gives us less than equals that, which means we need to look at 50. There's 50 values, and of course, if they're all 0, it's very, very unlikely that's a random sequence. Okay. So in the case of 0 to the omega, we note 0 to the omega passes this test for every omega greater than 0. And we take this as a justification that 0 to the omega is non-random. Whatever threshold of error we choose, we can detect non-randomness of the 0 to the omega after that. Take this. Questions or observations at this point? Right, very good. Yeah, that's exactly the observation I was hoping for. Of course, we can modify this test here for any infinite word q to begin with, and where instead of, any infinite word, suppose we've got some fixed infinite word, omega word p, and we, at this point, test whether our input sequence q is equal to p to the n. So actually, we have a way, according to this notion of test, which I haven't quite given with the general notion, but something like this is going to say that every infinite sequence is not random, so it looks like a non-starter. And of course, then this is where computability theory is going to come in, because computability theory is going to say, well, actually what we want is to have such a test that we can give an algorithm for. Okay? So here we can give an algorithm, because for any n we can come up with, what we're testing is 0 to the n thing. Whereas if we started off with if we were putting the finite prefixes of a given fixed infinite sequence p in here, then we would only be able to do that if p were a sequence. So I'm jumping ahead in the notes here because I wanted to give a more elaborate example of a computable test, but okay, but no, it doesn't matter. I won't write it. Okay, let me give a more elaborate version of a non-randomness test. Or elaborate non-randomness test. So probability theory, there's a very famous result called the law of large numbers, which has a weak version and a stronger version. It's more general than just fair sequences, but we'll just do the version for fair sequences. So law of large numbers in probability theory says that the probability that infinitely generated, but a sequence generated by a coin toss little p satisfies the property that we take the limit as n tends to infinity of the averages of the first n values of the sequence. So we have the sum from I equals 0 to n minus 1 of, let's again use q for our input, of qi. So we're taking the average of the first n values of the sequence q, where the probability is this q is generated by infinite coin tosses. Then as we look at longer and longer prefixes, probability that the expected value, sorry, there should be a 1 over n here, like that, taking the average, the expected value, if you like, of is a half. So there are, asymptotically, as one goes to infinity, there are roughly the same number of zeros as there are of ones. Sequence. Position that a bit more nicely. So you can think of, this is a property that random sequences almost surely satisfy. So you can think of the negation of this property as something we might use to detect non-randomness. So a sequence is kind of looking non-random if it doesn't enjoy this property that as the length of the prefix tends to infinity, there are roughly the same number of zeros and ones. Okay. So we look for so we'll say an individual sequence Q satisfies law of large numbers if let's just draw a red balloon around this. It's not the probability statement, but just if what's in the red bubble holds. So in other words, if this sequence of averages converges and its limit value is a half, that's what that means. Okay, so it satisfies LLM if it indeed does have the expected property that we would get from a random sequence. Forgot to move the ball, the camera. So we want randomness tests to show that to sort of detect as a symptom of non-randomness the failure of this property LLN. Is the LLN is characteristic. Okay. So if Q does not satisfy LLN, it's not. And what that means is just negates the definition from Annalisa Ehner of what it means for a sequence to converge to a limit. And we have, and for some delta greater than naught, this the sum of the average over prefixes differs from a half by at least delta for infinitely many prefixes. So I've got in my notes this n mean P instead of Q minus a half. Right. Oh, let me just write n mean while the camera is on this panel rather than that. So n mean of Q is exactly this value there. So not the limit, but the sum, just the mean of the prefix. The first n values. Here we have n minus 1. Okay, that's n mean Q. And we can move the camera. That's going to be, it's going to be differ by more than delta for infinitely many. So we can detect its non-randomness by we choose a delta, which is the delta and with respect to that delta, we're going to detect the non-randomness, and we're going to give a non-randomness test that approximates this property for that delta. Okay, so given delta, a chosen delta greater than naught, we have following non-randomness test. So we're going to define a sequence of test properties, and once again, depending on our error threshold, epsilon, we will then choose an appropriate one of the test properties to satisfy. So we define our test properties are, call them T sub n. That's going to be a set of all infinite sequences Q, such that for at least we're looking in the end for infinitely many large deviations of the prefix average from a half, and the nth property here is going to look for at least n deviations from the property of a half. So it's for at least different values of I, or at least for at least n different values of I, we have that the difference between the I mean u and the half is greater than delta. Okay. So this inequality is violated at least n different places. And we observe that if a given we're given an input sequence P, an infinite sequence P, and we want to verify that it satisfies this property, we can semi-decide this because we just go through all different prefix lengths looking for violations of this inequality. And each time we get one, we say, okay, we've got one. And if we find n different such places, we then say, yes, we'll return. If we don't find n different places, well, we keep on looking. So it's a semi-decision property, but it's a semi-decidable property. So this is a semi-decidable property in the sense of the lecture on topological properties of computability on infinite sequences. Okay. Well, it's even an open property. Sorry, an open implies, sorry, semi-decidable implies open. It's a semi-decidable. But it also holds that if we consider each of these sets of sequences, if we take the intersection of all of them for all n, we get the sequences that have this that have this bias property that this inequality holds for infinitely many n. We take the intersection of all of these. And the probability that that holds for an infinite coin toss is 0 because of the law of large numbers. So that means that we take the limit, n tends to infinity, of the probability of an infinite sequence landing in T sub n, then that's 0. Because the probability 1, an infinite sequence will satisfy the law of large numbers, but when it does, it will fall outside of T sub n. It will eventually fall outside T sub n. So again, for any epsilon greater than 0, our error threshold, don't mind making a mistake in our detection of non-randomness, as long as it's a very unlikely mistake. Find n such that the probability of Tn is less than epsilon. Probability of being randomly in Tn is less than epsilon. And then we semi-decide if Q belongs to Tn. And if that semi-decision procedure says yes, Q belongs to Tn, we say, okay, we're looking very non-random because we've got so many large deviations from a half of the prefix average that up to it's very, very unlikely that would happen. That such a randomly generated sequence will satisfy the law of large numbers, and it's very unlikely that we would get so many violations insofar in the distance as far as we've gone. And in fact, using some probability theory techniques, one can work out for an epsilon, one can work out what's an appropriate n to look at. But let's not go into that's kind of probability theory, so we're not going to look at that. But anyway, this so
one attached to probability of Tn.
Right, so the probability of Tn is the probability that, I mean, we will actually give some definitions later, but it's the probability that if we randomly generated a cube using coin tosses, then it would land inside T of n. Okay? So it's actually the probability of the uniform probability measure on the space of infinite sequences, which is the standard thing in probability theory. And so, if a sequence satisfies star, if an input sequence Q star that is for our chosen delta, it really does, we really do have infinitely many deviations, delta deviations from a half, then it belongs to the intersection of all these test sets. So whatever tiny epsilon probability of error threshold we give it, if we apply the appropriate test, we will detect that the sequence is non-random with that probability. So we can detect failures of the law of the large numbers. So we're also going to expect every random sequence to satisfy the law of the large numbers. Okay, so let me just then give the abstract, having motivated it, can now give the abstract notion of test, of non-randomness test. A naive, because of the problem that we discussed earlier, about we're going to classify every infinite sequence as non-random. Naive non-randomness test is sequence Tn of subsets of infinite sets of infinite sequences such that, so firstly, every Tn is open. So that was the case in what we were looking at. They were semi-decidable, hence open. So we might strengthen this to semi-decidable, and in fact we will. But this is the naive test without building any computability theory in. And secondly, the limit as n tends to infinity of the probabilities of the Tn. Actually, I'm going to switch to the notation of the notes, which is lambda for the probability, because we're going to consider it as a measure, and lambda is the usual symbol for the Lebesgue measure, which is equivalent to the Lebesgue measure. But this is just saying the limit of the probabilities is 0, where lambda Tn is the probability that a fair random sequence, randomly generated sequence, lands in Tn. And we say that there's a sequence Q in 2 to the omega, 2 is set 0, 1. Satisfies the test if it belongs to the intersection for every n it satisfies the test for n. And the idea is, again, what we do is, given an epsilon error threshold, we find an n such that the probability is less than epsilon. We then look to see if our Q belongs to that Tn, and because Tn is open, if it does belong to it, we can kind of get that information in a finite amount of time, because there'll be some prefix that all extent, if it belongs to the set, there's some prefix such that the cylinder of that prefix is contained in the open, so we only need to look at that prefix like. Okay, and that would be a notion, that's kind of the naive notion of non-randomness test. We've already discussed, with this definition, every infinite sequence is non-random. And so what we're going to do is we're going to, in the next part, build computability theory into this in such a way that we get a nice definition. And in fact, the way we do this, which is due to Martin-Löf, is very good motivation as well. It's kind of intrinsically motivated. It's not just solving a problem, it makes sense in its own right. Okay, are there any questions on that? Not from that side of the room, not from this side of the room. Okay, right, well, the clock on the back wall is slow, but by the clock on the back wall, it's exactly 3 o'clock, so we'll start again at 1:15 by the clock on the back wall. Okay, so this is the naive notion of test, and as we've already argued formally, we think of this as a way of detecting non-randomness. Such a test provides a test for non-randomness. We would say a sequence is non-random if there's some non-randomness test which detects it. And as we've already argued informally, every infinite sequence is going to be non-random according to this. That's written out in detail in the notes. We already discussed it, so let's not do that here. What we want to do is correct it, and correction is Martin-Löf's definition. So we're going to have a Martin-Löf non-random test. Let's write ML. Wrote Martin-Löf's name down once. Non-randomness test, or it's Martin-Löf test for short. That's how they're normally known. We want to make this. We want to put computability theory in, so that that our test is something we can actually carry out. If we're given an infinite sequence as a stream of input bits, then we can actually detect the non-randomness of it by applying the test. So instead of every Tn is open, we want to make every Tn semi-decidable. I'm going to use more computable topology terminology, but it's equivalent to semi-decidability from the lecture on computable topology. That's a few lectures ago. So actually, instead of semi-decidable, there's another equivalent terminology, and we'll look at it in a moment, called computably open.
But moreover, we want to be able to find the right semi-decision procedure to apply given an epsilon. So from an epsilon, we need to find an n such that the probability is less than epsilon. And given that n, we need to be able to get the semi-decision procedure from the Tn from n, usefully. So the second bit, getting the n from epsilon, is we ask for this convergence, but with a computable rate of convergence. Second part, we want these to be computably open, so they're semi-decidable, but also we want to be able to get the algorithm for semi-deciding from an n. What that means is that this sequence needs to be what we're going to call a computable sequence of computable open sets. So the sequence T and sub n is a computable sequence of computably sets. And we can make the main definition. Sequence Q not random, just ML random. If well, it's non-random if there exists a Martin-Löf test that detects its non-randomness. So it's random if it does not satisfy any non-randomness test. So if it, or another way of saying that, if it fails every ML test. It's not the intersection of any Martin-Löf test. It's not in this sum. We can find some sufficiently high threshold, sufficiently small threshold that will detect that. No matter what, how small threshold we get. Never mind this. So every test it does not satisfy. Right. So let's. With a naive notion, we have that every sequence is non-random, so there are no random sequences. So can we do it better in this case? How can we prove that there are random sequences? Well, we'll come to that in a moment. Let's first look at a very simple consequence of the definition that a computable sequence is never random. So proposition, computable sequences not, which is what we were expecting from the beginning. That's a deterministic algorithm, so on them to count, especially. And the proof is now similar to what we had for showing that 0 to the omega is not random according to the naive definition. Because the sequence is computable, it works according to this definition. So the proof, I'm not going to give a full proof in detail, but I'm just going to say, let P be a computable sequence, then then the sequence of sets of all those Q infinite sequences only the words of zeros and ones, such that the nth prefix of Q is the same as the nth prefix of P. This is an ML test. It's just like in the very first example, the zeros, probability of this set is 2 to the minus n. So this is the cylinder set. Oh, this is just the cylinder set for the nth prefix of A. So I guess probability is 2 to the minus n. We know that these are open sets. We haven't given the definition of a computable sequence of computable open sets yet, but it's quite intuitive that this is one. It will be very obviously when we give the definition. And moreover, we have that P satisfies this test because obviously it's in the intersection of one. Okay, so computable sequences are non-random. So if we want to find actual random sequences, we need to go outside the set of computable sequences. And to get further information about non-randomness, I'm just wondering, yeah, it is pretty much so we still haven't given the definitions here, but I think what I want to do is do some more. I mean, the notes go to slightly different order, but I want to do some more conceptual material, then get to the technical definitions that back it up. And, hopefully, we'll get through the conceptual material without needing too much definitions. Right. So to get further information, what we need is somehow what's the main result for today, and that's going to be proved in the third hour. The nasty technical work till the end, but it's a theorem, and this was a beautiful theorem of Martin-Löf from his paper where he introduced the random sequences. Which was the 1966 paper, so nearly 60 years old. It's a theorem of Martin-Löf. Which is, there exists a single universal Martin-Löf test. What does that mean? So a computable sequence of opens is a universal ML test, so this is the definition. If P not ML random implies P satisfies TU. Remember, not ML random means satisfies some Martin-Löf test. So if a sequence satisfies any, if it satisfies any one Martin, if it satisfies any Martin-Löf random test at all,
then it satisfies the universal test. So this universal test detects non-random, just, if we want, it's a single test that will always detect the non-randomness of a sequence. So it includes our test that the sequence is different from 0, infinitely many zeros. It includes our tests that the sequence is different from any, that the sequence, so random the sequence is different from any computable sequence. And it includes our tests for the sequences violating the laws of the large numbers, law of large numbers, and so on. Yeah, it includes all tests. Okay, so it's a beautiful and powerful result, and the proof, but the proof is a bit technical, so we'll do the proof at the end of the lecture. It's a kind of, you know, it would be nice if there was something practical like this, because, you know, in practice, pseudo-random number generators are really important for all sorts of applications, and there's all kinds of theories about what sort of tests to apply to random number generators to see that they do indeed generate well-behaved random sequences of pseudo-random numbers with very good properties. And you know, this kind of gives one the hope that one could just have a single test that one could apply and would always detect if a pseudo-random number generator wasn't doing its job properly. Something like that. But unfortunately, it's, well, anyway, it's about infinite sequences rather than finite ones, so it doesn't really apply to that. But also, you know, when one goes through the definition and thinks about it, this thing would be horrendously inefficient to try to apply. Anyway, we'll see kind of a little bit how the definition works at the end of the lecture. But once we've got this beautiful fact, oh no, yeah, the other thing that was the thing that was on my mind to say that I kind of forgot at the time was, although it looks surprising in this context, we're sort of, this is a course on computability theory, and we're a little bit used to now in computability theory, when we have a notion, there's quite often a universal such notion. So we have universal Turing machines, universal computable functions. We had a universal something last week as well. We had a universal prefix-free function last week, and so on. So anyway, we have the universal Martin-Löf. And as a corollary to get nice properties, so firstly, set R standing for random, so ML standing for Martin-Löf random sequences. So that's set of all infinite sequences such that P are random. So the non-random sequences are given by a universal test, and this means that the complement of RML, R sub ML, the set of sequences not in RML, that's the set of sequences that satisfy the universal test. So that's intersection. Those that satisfy the test, those that satisfy all tests for whatever n in the universal test. So the larger n is for smaller threshold epsilon. So this is a countable intersection of semi-decidable sets, computably open sets. It's a countable intersection of open sets. So its complement, which is Martin-Löf sequences, is a countable union of closed sets.
expression F sigma sets. So we had G delta sets a few lectures ago. The F sigmas are the complements of G delta sets. So it's not an open or a closed set, but it's not too far. It's a fairly simple set. So one can consider the probability that a random sequence lands in this set, and the probability is what? What's this? Well, the probability of being not random, well, this is an intersection of these open sets, but we were requiring here that the probability of these tends to 0, and so that the probability of this intersection equals 0 because of that. And if the probability of this set is 0, the probability of the complement is 1. So this is saying if we generate a random sequence randomly, then we have probability 1 of getting a Martin-Löf random sequence, which, you know, the definition is correct, it should satisfy that property, which it does. And as a consequence of that, well, a set, it can't be an empty set if it has probability of 1. In fact, it has to have cardinality of the continuum. So 3 are 2 to the other 0, many ML random sequences. So we know it's a non-trivial, set, as with many instances, it enjoys some good property with respect to the probability theory. It correctly rules out computable sequences. Moreover, it has a plausible definition based on this idea of essentially statistically detecting non-randomness. The statistics here is to do with this error threshold epsilon. That's a kind of typical feature of the statistical test, that statistical test, you give some epsilon that you want to, you know, like your p-value in a statistical test from standard scientific statistical tests. You give a p-value, which is a small value of error that you're accepted to tolerate, and for any p-value we can detect, for any epsilon, the small value of probability of error, we can detect non-randomness of that error. Right, good. So there's one more conceptual bit that I'm going to leave right for the end of the lecture. Apart from that, it's time to roll up our sleeves and get to the so let's actually do that and get to the technicalities. So I've skipped various bits of technicalities as I went along. Let's see. Let's start with the definition. So we've got a computable sequence of computably open sets and a computable rate of convergence. So let's start with those. Maybe rub off the definition. I think it was lecture 11 on the topological aspects of computing with infinite data. Called factor 11 that the set of infinite sequences is open if it can be expressed as if it is a union of cylinders. That's one way of defining it. There are many equivalents in that lecture. If it if this is simply saying if it can be expressed as the union of cylinder sets. And this includes the energy set. The energy set is an energy union. So I think actually the first thing I'm going to do is define the probability measure that we're using. And we're only, in our definition, we only needed probability measure for open sets. So I'm just going to define it for open sets, although in the end I did say that the sequence of Martin, I did say that the set of Martin-Löf random sequences has probability measure 1, and that's not an open set, it's a countable union of closed sets. But anyway, once one's defined the measure on open sets, it's not hard to extend it to Morel sets. We actually expected, but for those of you who know some measure theory, actually once we've got the measure defined nicely on cylinder sets, you can extend it to Morel sets. But it's very easy to define the probability measure for open sets, because actually one can prove that if a set is open, then it can be written as a disjoint union of cylinder sets. So in general, if you've got a union of cylinder sets, they might overlap. You can always make that disjoint. There's a proof of that in the lecture notes. It's actually a quite fun thing to think about, so I won't do it. It's a nice exercise. Prove that. So it holds that every open is a property that's nice to prove. In this case, every open set can in fact be written as U is, so I just simply write that. The plus here means disjoint union. So it's disjoint union open sets. But you might need to change the family here because otherwise they might not be open. Okay. So given this, disjoint union of open sets, how do you think we can define the probability measure of an open set? So first we'll define the probability measure of the cylinder set. So what's the probability of a cylinder set? Probability that randomly generated sequences in the cylinder. Okay, so that's 2 to the minus the length of the. So if we have an open set, U, expressed as a disjoint union of cylinder sets, so this is probability of a cylinder set. U. So what's the probability of an open set? U. How can we get, whoops. How can we define that? Right, so we express it as a disjoint union. And when we've got a disjoint union, those of you who've done measure theory, then the key property of a measure is that the measure of any disjoint union of sets, well, the measure commutes with the disjoint union's sum. The measure of the disjoint union is the sum of the measures of the sets. So this is just the sum of two to the length of minus the length of wi if U is written as a disjoint union of i's. And this I is always countable, but this set I is always countable because they're only countably any cylinder sets to begin with. Okay, is this obviously well defined? What might be problematic? Yeah, but there isn't a unique way of writing U as a disjoint union of cylinder sets. So you can write it in many ways, but you can prove that however you write it, this sum is the same. And that's a fun property to prove, right? It's not straightforward at all to prove that, but it's not, it can be proved purely constructively as well. And I don't know if, I don't think there are any hints in the lecture notes about that, but it's a fun thing to do. Okay, so now we've defined the probability of open sets, and we're happy with that, because we'll just accept that that gives an unambiguous definition. So the next thing to do is to define computable sequence of computable open sets. And the notes, I think the notation's a bit heavy-handed. I'm doing everything in terms of type 2 representations, and it gets a bit heavy. So let's try and do it just intuitively in the lecture. So we're going to use the fact that every open can be represented as a union of cylinders. Now we're going to go back to arbitrary unions, not disjoint unions. These unions are at most countably infinite. They could be finite, it could be empty to get the empty set. Just for convenience in what's going to follow, I'm going to want to give everything as a countably infinite union. And basically, I'm just going to list the sets that we're unioning by listing the words, defining the cylinder sets. But to make things countably infinite, I'm going to run into problems with the empty set. So I'm going to give myself a symbol for the empty set too. So a computer, we represent. So in the lecture notes, I'm doing this using infinite words, but more simply, we represent open sets as infinite sequences and I think, what do I call these in the notes? Yeah, I call them little W's. So W1 and W2, where every Wi is either a word Wi in so a finite word over 0 and 1. In which case it's determining a cylinder set, or the symbol Wi is empty set. So we have a symbol for the empty set. Okay, and this
And this represents the union of WI's if WI is words and well, sorry, where we don't need to worry about the unions. So it's the union of set of all cylinders WI such that WI is a word. Okay, is that clear? So we represent it as an infinite sequence of words where we throw in some, which are the cylinders generating it, but we allow ourselves to throw in some empty set symbols if we want to. Partly so we can represent the empty set, but also because it's going to be useful to have these empty set symbols later. Okay, so now this bit is where the later lecture notes really get unnecessarily heavy in notation, and the idea is the same as what I'm going to say. So an open set is computable if what? Any guesses? Sorry? Not, it doesn't need to be finite. I mean, so the set itself will never be finite unless it's empty. We don't want the sequence to be finite either. I mean, the sequence, a finite sequence that is empty on everything but all but finitely many, that will always determine a clopen, because it will be a finite union of clopen sets. In that case, because every cylinder is clopen. So an open set is computable simply if it has an infinite word representing it as a computable word. So if it is represented by, or sorry, rather than infinite sequence, by some computable infinite sequence. Okay, so very intuitive. And, you know, there's not that much point giving you so many gratuitous exercises that none of you are going to have the time to do. But, you know, if you ever did feel like, you know, you woke up at night and were totally bored and wanted something to think about, it's quite fun to prove that this definition of computable open set coincides with semi-decidable set from lecture 9 or was it 10 or 11. So the computable open sets are exactly, these are subsets of 2 to the omega are exactly the semi-decidable sets. It's quite easy to show that the computable open set, according to this definition, is semi-decidable, but the directions are a little bit more fun because you have to convert a type 2 Turing machine into something like this. Okay, so that's a computable open set. What we actually need is a computable sequence of computable open sets. So let's move to another board. A sequence of open sets let's say, Tn now. That's what I was calling them earlier, but T is not important. Is simply represented by a sequence of sequences. So we have, let's call it W00, W01, W02. So this represents T0. W10, W11, W12, W13 represents 1, W20, W21, W22, W23 represents T2, etc. The when is a sequence of open sets given by such a representation. When is it computable? Well, of course, using the pairing function, we can represent this as a single sequence. And it's just if that single sequence is computable. So Tn is a. And if the single sequence is computable, every horizontal sequence is then computable too. That follows because you can just project out. So, the requirement of the single sequence capturing, going down the diagonals, capturing the whole of this table, requirement that that's computable gives us that every sequence and every open in the sequence is a computable open, but we're getting them in a computable way, so it's a computable, but it's justifiable to call this a computable sequence of computable opens. So Tn is a computable sequence of computable opens if a single sequence representing Wij above using the pairing function is computable. Finally, to understand the definition of Martin-Löf random sequence, we also have the notion of a computable rate of convergence. A computable total function I think I call it R in the notes, but let me just check. Yeah, R N is a beautiful rate of convergence or and I'm just going to deal with the case we need, in which we're only dealing with probabilities converging to 0. So we have the convergence of a sequence of non-negative real numbers to 0. I mean, it's easy to modify this to give the general definition of convergence, of rate of convergence, but we just don't need the extra generality. So for a Cauchy sequence in the interval, closed interval 0, 1, which are by probabilities taken from converging
to 0. So let's call this Cauchy sequence x sub n. If, and the point is that if we give any n, then R of n will tell us how far to look so that the Cauchy sequence, is within 2 to the minus n of 0. So if for any n and m greater than or equal to R of n, it holds that we have that converging to 0 and the number's non-negative, so we don't need any modulus side or anything, we just have asked for x sub n for all n beyond n to be so beyond R of n, all n beyond R of n to be small 2 to the minus n. Okay. Now we have a complete definition of, given the definition of all the ingredients that go into Martin-Löf random sequences. So again, it's exactly 4 o'clock by the clock on the back wall. Just to say, the third hour is going to have with the proof, which is quite technical in the notes, but I'm going to try and do it by pictures of the existence of the universal Martin-Löf test. And then we'll just end with a little bit of more conceptual material, and just because it'd be nice to unwind a tiny bit after the technical proof. Are there any questions before we break? Right, good. So it starts again at past. Okay, so what I want to do is outline in a more informal way than in the lecture notes the existence of the universal test. So existence of the universal test. So the first step is that there exists a computable function. I'm not going to give these functions names because I don't know what names to call them, but we'll just refer to them by what they do. So from natural numbers, to representations of computable sequences of open sets, computable sequences of computably open sets. Surjective. Surjective onto computable sequence, not onto representations. We don't get every representation in this way, but we get every computable sequence of computably open sets. And we get some representation of every computably sequence, every computable sequence of computably open sets onto computable sequences. I'm not going to give you any of the details of this, except to say that holds for the following reasons. So we're representing computable open sets as infinite sequences
of mixed words in the empty set symbol, it's not difficult to show that such things are in one-to-one correspondence with computably enumerable subsets of the set of words. One-to-one, again, meaning not one-to-one on representations. It's not that the sequences themselves are in one-to-one correspondence with the subsets, but for every sequence, one can get the corresponding subset of words, and from every computably enumerable subset of words, one can generate back a sequence that's potentially padding it out with empty set symbols, but that gives you the same open set. And to get that via a function from the natural numbers, we essentially use that we have these enumerations of computably enumerable sets, the W sub E and the E sub E representation. And we use the trick to get back to the versions with the empty sets put in, or with repeating symbols. Another way of doing it, we do need to stick some empty sets in general. We do essentially the construction that gives us non-empty computably enumerable sets as images of total computable functions. And then you do a modification of that to get the computable sequences. So that's as far as I'm going to go into that. The second thing is we're going to convert a representation of a computable sequence of computably open sets into a Martin-Löf test. So the next function, that's so 2, goes from computable representation of computable sequence of computably open sets to Martin-Löf tests in such a way that if the computable sequence of computably open sets is a Martin-Löf test to begin with, we get it's preserved. Okay? Preserving Martin-Löf tests. If the argument that's given is a Martin-Löf test, then we get back Martin-Löf test. So our input is a computable sequence of computably open sets. It's a computable sequence, so let's call these computably open sets T0, T1, T2, T3. And it being a computable sequence means that we have a sequence of words or empty set symbols whose union, so that the union of the things is this computable open set. So that represents T0. Yeah, so there's a little lie here. So as I've been reorganizing my lecture notes, and now I'm beginning to realize why I did them. It's a bit like last week. I'm beginning to realize why I did this in the order I did in the lecture notes. There's a tiny lie here, but still we'll go with this. I mean, this time at least I'm sharp in my mind about what's going on and where the lie is, and stuff in this message. The lecture presents things in this way. So it's a computable sequence of manual tests. It's given by sort of this data in a table, which is presented as a single sequence. We want to convert this into a sequence of ML tests. So what we do is we simply copy the data. W00, W01, W02, W03, But at some point, we switch to empty set symbols. And we copy the data as long as, so we've got a finite set of empty set symbols and words here. We copy the data while the probability of the unions of these cylinder sets, so I'll write them as if they were all cylinder sets, although some might be the empty set symbol. Yeah, there'd be dot dot dots, and I've only got 4 of them. So we copy them while this is less than or equal to, in this case, well, which it always will be, 2 to the minus 0, because we're in level 0. Here we copy them, suppose it goes to here, and then we replace with, then we start replacing with the empty set. So we copy them while the union of the probability of all of them is less than or equal to 2 to the minus 1. So lambda of the union of those is less than or equal to 2 to the minus 1, so half. And maybe this one kind of goes on a bit further, who knows? 2, 4, 2, 5, 2, 6. Maybe only at this point we need to put an empty set in, then we keep on going with empty sets here. So here, while the probability of the union of everything so far is less than or equal to 2 to the minus 2, here less than or equal to 2 to the minus 3. And as soon as we get too large, we start returning empty sets. So what we're doing is we're making sure, we're ensuring that a transformation of t0 to say t prime 0 has probability here less than or equal to 2 to the minus 0, which it always will have. Here, the transformation of t prime 1 has probability less than or equal to 2 to the minus 1. Here, the probability it's less than or equal to 2 to the minus 2, and so on. Actually, it's not true that we preserve ML tests in general, but we preserve what we're going to call rapid ML tests, where an ML test is rapid. So I'm going to use Tn for the ML test if probability of T of n is always less. So we don't just have a computable rate of convergence, but we have a specified rate of convergence that's converging exponentially fast. So in other words, the identity we have the identity as the rate of computable rate of convergence. And we're going to have another relevant phrase here, which is an ML test is decreasing if the sets literally get smaller in terms of subsets. Okay, so here there's no way here we're not getting back decreasing tests necessarily, but by the construction this we always get back a rapid ML test, and if we started off with a rapid ML test, we get a rapid ML test back. Okay. Observation 3, or ingredient 3, is that we can convert any ML test into a rapid decreasing test. Three
have a function that takes us from ML tests to representations of ML tests to rapid decreasing ML tests. And that this preserves you start off with a rapid decreasing ML test, we preserve the ML test. Well, in fact, more generally, the important thing is that it preserves the set of sequences that satisfy the test. Preserving the set of sequences that satisfy the test. And this is very easy because we start off with an ML test, so a T0, a T1, a T2, T3, so on. So it's a computable sequence of computable opens. And these come with a computable rate of convergence. And we map T0, T0, intercept T1, intercept. Well, so we map this sequence rather to, and we go as far as T, well, in this case, it will always be T0. Let's write it like this. We go to Tm, where m equals R0. So m is such that from all points on in the sequence, the probability of T of m is less than or equal to 2 to the minus 0, which is 1. I mean, it's not giving us any information because here we've got, but here we go to, let's call this m sub 0, T m sub 1, where m1 equals R1. I should have said the rate of convergence function is an increasing function. I think I said that. Here we go to M2, where M2 is what we get from the rate of convergence of 2. And the point is that we can computably intersect open sets. That's an easy thing to do on the representations. That's also a fun exercise. So if you're waiting in the middle of the night and want to do exercise this, easier than the previous one. In the previous exercise. So we can intersect, we can form representation with the intersections, we can easily compute, we've got the bounds given here. So we're forming a finite intersection, and by construction, R is an increasing function, so this is a decreasing set of sets, so each lower one is a subset of those above it. And by the definition of the rate of convergence, we're intersecting with a set whose probability is less than 2 to the minus the level we're in, and so the intersection is only smaller. So this satisfies this. So we've got the decreasing property and the rapid property, and also and it preserves the set of sequences that satisfy the test. Okay. So, because of 3, we know that we can redefine Martin-Löf random sequence. So by 3, sequence P or Q is ML random if and only if it does not satisfy, but it fails every rapid decreasing test.
So it's enough to find a universal test that has the same power as rapid decreasing tests. All right? And now what we do is we put 1, 2, and 3 together. So we start off with a natural number. It takes us to an arbitrary sequence of computably open sets. And all sequences of computably open sets are in there, including all rapid ML tests. So every rapid ML test is in there. We then convert to every rapid decreasing ML test is in there. We convert it to a rapid ML test. And if we started with one, we're preserving it. So we still have, so now we have an enumeration, a surjective enumeration of rapid ML tests that preserves rapid decreasing ML tests. And then we map it along with this. We've got an ML test, and now we get back an enumeration of rapid decreasing ML tests that still preserves the rapid decreasing ML tests that we started with. So we've now got the point is this gives us a computable sequence of rapid ML tests that contains every rapid ML test. So putting 1 to 3 together, let's just write on the board what we did. Between 1 to 3 in that sequence, in combination, we have a computable function, so enumeration. So the rapid decreasing ML tests that is surjective in the sense that for every rapid decreasing ML test, or even for every rapid ML test, or even for every ML test, there is some ML test in this sequence that has the same set of sequences that satisfies that test. That is surjective in the appropriate sense. Okay, so now we can construct our universal test. Because if we look at this enumeration of rapid decreasing ML tests, well, we have the tests, call them, let's start with, so we're enumerating, so we'll have the tests T0n, that's the first one in the enumeration, the tests T1n, test T2n, test 3n, and so on. And we can write this, so the first test, it's a computable sequence of opens, starting with T00, it's a decreasing test, so we have a subset of that, that's T01. Oops. And a subset of that is T02, a subset of that is T03, and so on. That's our first test. We have the second test, so decreasing sequence of computable opens. Seem to get the index wrong here. It's T11, T12, T13. It's always a question, it's like how big a table does one want to write when it's an infinite table. Well, that's maybe T21,
2, 3.
Let me see what other information that was.
Maybe let's do one more. 2, 3, 0. 2, 3, 1. 2, 3, 2. 2, 3, 3. And each of these tests is decreasing, as we can see. I've written change of subset inclusion, and it's also rapid. So here we have lambda of what's in this row, but each thing is less than or equal to 1. Here, which it obviously is, but here it's less than or equal to 2 to the minus 1. Then less than or equal to a half. Here it's less than or equal to 2 to the minus 2. Here, the probability is less than or equal to 2 to the minus 3, and so on. So what we can do is we take a union along this diagonal here. So T01, T12, T23 seem to be a straight line for some reason, but it should be. And so on. And the union of this, well, the probability here is a half, a quarter, an eighth, at most a 16th, and so on. So these are going to add up to something less than or equal to 1. And the next one, we take this one, and we start off with a quarter, an eighth. So the probabilities are going to add up to less than a half. And these unions are obviously decreasing because everything we've got here is a subset of everything here. And we can see by the definition that it's rapid. And we can compute the unions because we can compute this whole table. So, and it's clearly combining all the tests. So T universal sub n is the union from I is 0 to infinity of T so Ti of I plus n plus I plus 1. Just see if that's what's in the notes. Yep. Is the required universal NL test, and it is rapid decreasing construction. This is also but it's universal because if we have a sequence that's non-random, then the sequence will be contained in one of the vertical intersections. And if it's contained in one of the vertical intersections, it's clear that it's in the union of all the diagonals. Sorry, it's clear it's in every diagonal, so it's in the intersection of all diagonals. Right, good. So that's as much detail as I wanted to give of the proof of the existence of the universal test, and I think it's kind of over detailed in the lecture notes. Making too much use of representation. Like too representation. Right, so the last thing I wanted to say is So we know there exists a Martin-Löf random sequence. Can we actually find one? Well, we can toss a coin infinitely often, and the result we have about the measure says almost surely that infinite sequence that we generate will be a Martin-Löf random sequence. Well, that's not very helpful because firstly, we'll never finish generating the sequence. Secondly, what does almost surely mean? So what about, can we find an explicit example? We can, and in fact, it is P omega, the sequence that's Chaitin's halting probability from last week, is an example of an explicit example of an ML random sequence. Why does this hold? Because of the following very beautiful result that I would love to have a lecture course with actually 2 more lectures, because there's some material on the core computability theory, including Kleener's recursion theorem, that I omitted earlier in the course, which I really love and would love to. So if we had 15 lectures, recorded by the time, I mean, obviously I could have a lecture on Monday next week, but I think this is enough. But if 15 lectures are naturally fitted in, I'm going to put that in. But if there were a 16th lecture, which there never will be, then I think the proof of this theorem, there might not be any audience for it, but the proof of this theorem would be what would go in. So I think this is a really stunning result. The theorem says the following are equivalent for any infinite sequence Q. Here belongs the omega. The first statement is Q is ML random. Second statement is Q is prefix-free incompressible. This is I think a lovely result, because it says that randomness is being studied today. So it's a form of saying the sequence is random in the sense that if we try to detect any statistical anomaly of the sequence not being random, so it doesn't have any statistical anomalies that are symptoms of non-random. We can't statistically detect any non-randomness. Whereas this prefix-free incompressible is a kind of another notion of randomness intuitively, because it's saying that Q does not have any patterns in it that we can use to compress the description of the sequence. And it's quite a deep result. So this is due to Schnorr from the early 1970s, I think it was, I believe. Not completely sure. But anyway, it's a lovely result, and it connects the 2 topics from last week and this week and gives a fitting conclusion. So I'm going to end there. Are there any questions before I stop the video? Right, so let me stop the video. So thank you to online people for your participation online.